So objective 3 is to apply the concept of marginal analysis, and this is something from economics. So marginal analysis, we're looking at the rate of change and we're calling it marginal. So the rate of change of the cost function is called marginal cost. So rate of change is generic, but then when interpreted in different scenarios, it has different names for what it's telling you. So if you're finding the rate of change of a revenue function, then you're finding marginal revenue. If you're finding the rate of change of profit function, you're finding marginal profit. If you're finding the rate of change of a distance traveled function, you're finding speed. So rate of change is general, and then it depends on the context. And in our context, we're going to call the rate of change the marginal quantity. So if you're a linear function, your rate of change will be the slope m. And then we're going to get more complicated. But at first, we're just going to look at linear functions so we can study this concept of marginal quantity. So the marginal cost is the cost of producing one more than you were already producing. So if you increase production from 700 to 701 units of whatever it is you're making, the increased cost is the marginal cost at 700. So you take the marginal cost function that you find, and if you plug in 700, you get just the approximate cost of increasing from 700 to 701. So just the difference, okay? And then marginal revenue, revenue from selling one more than you are already selling. Marginal profit, the profit from making and selling one more. So it's the difference between what you were doing at 700 and what's happening at 701. That difference is the marginal quantity. Okay, so let's look back at this example where we had a linear function, and remember a linear function is any one that can be written as y equals mx plus b. And do you see that this looks like a y equals mx plus b problem where y and c of x are interchangeable? Then we have a slope of 42.5 and a y-intercept of 80,000. So this is a linear cost function. So the marginal cost is the slope. And then remember, it's in units of y, dollars, units of x, books. So it's $42.50 per book. Okay, then what's the approximate cost of producing the 1,001st book? Well, it's $42.50 because it doesn't change when you're a linear function. That is the characteristic of a linear function. Each one that you add adds the exact same amount of cost. So the answer to the first part of C and the second part of C are both $42.50 per book. And I'm writing it in two different ways just so you can see and get used to it. Okay, then what's the total cost of producing 1,000 books? That's C of 1,000. So when you take your cost function and you plug in an X, you're getting the total cost. Okay, so think of this as a total cost function. So I'm going to replace X with 1,000 in the function. Use your function notation and write C of 1,000 to start. In general, tell me what you're going to do and then do it. So that's going to be 122,500. That's the total cost for making 1,000 books. Then objective 4, we're going to go back and talk about break even a little more because it's a really important concept. So a company can make a profit only if their revenue exceeds, is bigger than their costs. So you're profitable if your revenue is more than your costs. The place where they're equal is called the break-even point. Most businesses start off not making a profit, and then they get to the break-even point, and then they start making a profit. So you can either take your cost function and your revenue functions and set them equal to each other if that's what you're given, or if what you have is a profit function already, you can say, when is it 0? By setting it equal to 0 and solving for the x. So let's look at an example. The owners of a parking lot have determined that their weekly revenue and cost in dollars are given by R of x equals 80x, and this is in dollars. I just put little notes to remind myself because sometimes we're in hundreds of dollars or thousands of dollars, so I make notes to keep track. Then C of x is 50x plus 2400, and again this is in dollars. And x is the number of long-term parkers in their parking lot. Okay, so to find the break-even point, what we said up here was put the cost equal to the revenue. So let's do that. So we're going to put the cost, 50x plus 2400, equal to the revenue, 80x, and solve for the x, and that tells you when does that happen? When does break even happen? So we're going to solve for x by getting all the x's on one side. Then I'm going to divide by 30 to get x by itself, and x is 80 long-term parkers. So once you get up to 80 long-term parkers, you're at break even. And then if you can get past that, then life is even better and you become profitable. Okay, so this was kind of hard to graph on the same grid, so let me put a grid on my page here so I can actually have a grid, since for some reason these grids did not print. So I'm going to have a graph that has x is the number of long-term parkers. And then y is going to be in dollars. Okay, so you have two equations. Your revenue function is 80x. So that's the equation of a line with the y-intercept of 0 and a slope of 80. Okay, so whatever the scale is, we'll say when you get to 80 parkers, we could figure out that this is $6,400. So I'm eyeballing the scale here. Okay, then the cost function is linear. It has a y-intercept of 2,400. Okay, so that's somewhere down here, 2,400. And then it has a smaller slope. So it has a smaller slope. So it's going to end up intersecting the revenue function. And what we found with our algebra work was this break-even point where you have 80 long-term parkers, your revenue is $6,400, And go ahead and plug in 80 to the cost function, and you'll see that the cost is also 6,400. So this is graphically, by looking at the graph and seeing that when you have 80 parkers, your cost and your revenue are equal at 6,400. This was algebraically. Okay, so that was a refresh on break even. Really important concept, but we're not going to spend a lot of time on it because it's more algebra and economics, but it is in our curriculum, so we're covering it. Okay, then objective 5 is to use supply and demand curves to find equilibrium points. So many students confuse these two, so make sure you're filing them in completely separate areas of your brain. Break-even point is where revenue equals cost or profit equals 0. Supply and demand, it's got two different things going on. You have producers and consumers. So you have producers that are making things and consumers that are buying them. Well, the producers want the price really high and they want people to buy lots of them, but that's not how people behave, right? So from the producer's point of view, if the price is high, I make a lot of money on each one, but people don't buy as many. If the price is lower, I don't make as much on each one, but people will buy more of them. Then from the consumer's point of view, if the price is high, I'm not going to buy as many. And if the price is lower, I'm much more likely to buy more of them. So those are two really different conflicting points of view, and the equilibrium point is when they're in balance. So typically, lowercase p is used for price per item. So we use an uppercase P is profit. So make sure you can see the difference. I use a cursive lowercase p for price per item so that it looks really different from my profit function. Okay, so economists express supply and demand functions by P is some function of Q. So it's something over here, and we're just going to look at linear ones. So there's going to be a slope and a y-intercept, but Q is acting like X. And P acts like Y. So when you draw these graphs, you need to label them correctly. This is one of my things I'm fussy about. One of the reasons I want you to label the axes is it's not always X and Y. In this scenario, it's Q and P. So when supply and demand are in balance, that's called the equilibrium point, where supply equals demand, and everybody's probably equally unhappy, right? I mean, you're never going to be happy if you're a producer and you want to sell more. Okay, so here's an example where we have sugar, and we have that the supply is P equals 1.4 Q minus 0.6. So does this look like Y equals mx plus b? It's a linear function where Q is going to be on the horizontal axis and P is going to be on the vertical axis. Okay, so let me come over here and make my squares a little smaller. So I'm going to have the Q axis for quantity, and this is going to be in pounds because the price is in dollars per pound, so the quantity must be in pounds. Then the vertical axis is P, the price, in dollars per pound. So remember always that it's dollars per pound. It's not total dollars. Okay, so the supply, I have a negative y-intercept. So I actually start down here below the q-axis, and then I have a slope of positive 1.4. So this is P equals 1.4Q minus 0.6, and this is supply. So let's pause for a moment and think about whether this line makes sense, how it looks. What it's saying to me is if the price is high, people will buy this many. If the price is lower, people will buy, sorry, this is the supplier. If the price is high, the supplier will make a lot. If the price is lower, the supplier will make even fewer. If the price is really low, the suppliers make even fewer because they want to make more money, so they aren't happy when the price is lower, so they make fewer. Okay, so that's supply. Then let's look at demand. And if I think of this as y equals mx plus b, then I see that I have a y-intercept of 3.2, so $3.20 per pound. And then I have a slope of negative 2. So this line is going downhill, and this is the demand function, P equals negative 2Q plus 3.2. Now let's see if that function makes sense to you as the consumer. So if the price is high, you don't want very many. And then if the price is lower, you want more. And if the price is even lower, you want even more. So it makes sense that always supply is going to have that positive slope, and demand is going to have the negative slope. Okay, so we've done A, graph these on the same grid. Then find the equilibrium quantity graphically and algebraically. So here's graphically, and if I'd made a really accurate graph, then I would be able to read off of my graph my equilibrium quantity and my equilibrium price. My graph is not very precise, so I'm going to do it algebraically, and then I'll go back and put that on the graph. So finding the intersection point of two lines, recall, is the same thing as solving this system of equations. So I have two variables, P and Q, and two equations. So I want to solve this system of equations to find the intersection of the two lines, and that's going to be the equilibrium point. So this is a system of equations. One of the methods that we reviewed was substitution, where you could say, well, P equals this quantity, so let me substitute for the P in the other equation, 1.4Q minus 0.6. And then I can solve for Q because that's the only variable I have now. So let's use our algebra and add to Q. So I'll have 3.4Q minus 0.6 equals 3.2. And then I'm going to add 0.6 and have 3.4Q equals 3.8. Then divide both sides by 3.4. So it doesn't come out exactly, but it comes out about 1.18 pounds. So the equilibrium quantity is about 1.18 pounds if I'd made a really good graph. And you can use Desmos to make these graphs and then transfer them onto your paper after you see how they go. Okay, so that was B, find the equilibrium quantity graphically and algebraically. Then it says find the equilibrium price. Well, I have two equations that say what is the price if I know the quantity. It doesn't matter which one you use because we're talking about at the point of intersection when P is the same for both graphs. So let's just use the first one and say P is going to be 1.4 times Q of 1.18 minus 0.6. And I'm getting 96 cents per pound for the equilibrium price. So on my graph, this would be $0.96 per pound. Okay, so that's the equilibrium price. And then I really like asking this last question because it makes you think a little. At a price of $2 per pound, okay, so here's our equilibrium price of 0.96, so $2 a pound is somewhere up here. We're asking about what's happening up here. So let's come across and look at and the green line is the demand. So it would say the demand is somewhere over here when the price is $2 per pound. And then the supply is way over here. This is the supply is $2 per pound. So can you see that the supply is bigger than the price? So there's a surplus. And the other way you could do this is this first equation is supply. So you could put the $2 as the price and solve for the Q. And you would get Q is 1.86. And then you could look at the demand and put $2 for the price and solve for the Q. And you'd get Q is 0.6 pounds. So whether you look at the graph or the supply is way more than the demand. So there's a serious surplus of supply. Okay, so I'm going to stop there and I'll make another movie for the rest of the section.